Hello and welcome back to section 14. In this video we're going to look at example 2. Last time we looked at a transition on a circuit that had just resistors, and we saw that it happens instantaneously. To make things more interesting, we're now going to change that circuit. Instead of an 8 ohm resistor, it's going to be an 8 farad. But we want the same thing. We want to know what Vx is across those across that 8 farad capacitor. So I've built this over here in the simulator. We can look at it real quick before we solve it. So if I start this, what you'll see, so the green bar down here is the voltage, and it climbs slowly. So over here you can see that it's only 36. So by the way, 8 farads is huge. We don't normally work on 8 farads. We're working like 8 microfarads or 8 millifarads would be much more reasonable. And then so this thing's still charging. That's why the green bar is still going up. If I flip the switch here, now you see the current, the yellow dots, switch directions, and now this thing is starting to discharge. This is what I'm talking about when I mentioned transitions. So this is a very slow transition, and that's mostly because we have this very large capacitor right here. So let's see how long it would take, because it's going to take a very long time. I can tell you that right now. So let's go to our worksheet here. All right, so here's our circuit. We have our 10 volts, we have our 2 ohms, and now we have 8 farads, again, very large. We want to find V of x for t greater than 0. Now again, what's going to happen is we're going to turn this 10 volts off and see what happens. So that 10 volts, so if I redraw the circuit, plus minus. So I'm sorry if my hand gets in the way. So we have our 10 volts. We have our 2 ohms, and, oops, sorry, that should be 0 volts. That was the whole point of redrawing this. Plus or minus Vx and 8 farads. So it looks basically the same. All we did is we could have probably saved a step and just kind of crossed out that 10 like I did there. Now when you see one of these circuits, one of the first things you're going to want to do is identify what kind of energy storage element you have. So in these first order circuits, you're only going to have one type. It's either going to be a capacitor or it's going to be an inductor. You will not have both. So in this case, we have a capacitor. So we need to figure out what are our equations for a capacitor. So if you look back through your notes, you should find something that says that I equals C dV by dt. And the other form of this is V equals 1 over C integral I dt. And it doesn't matter about the capital or the lowercase I. I should be more consistent with that. All right, for our resistor, V equals IR. Hopefully you guys know that one by now. And we can rewrite that as I equals V over R. So in general, when you solve these circuits, we want to use the derivative form when possible. And then we want to match up the similar form for the resistor. So we're going to try to use I equals C dV and I equals V of R when we write out our equations for this. It just makes the math a little bit easier. You can do it with the integral, but you have to take some extra derivatives. Okay. So in order to do this, what we're going to have to do, oh yeah, by the way, those equations, hop back over here. So the current through the capacitor, that's what that is. And for the inductor, if you need that, the inductor equation, I'll just write it here, is I equals 1 over L integral V dt, or V equals L di dt. So we don't need that one. So we're going to use this one and this one up here. Those are the two we're going to use for this. Again, we want to use the derivative form when possible to make things easier. All right, so to do that, we're going to basically treat everything as currents and then sub in for voltages. So that is Kirchhoff's current law, or what we now know as node voltage. I know it's a little bit weird. So this node and this node, so if I label this node, I call this node 0. This is also node 0 now. We would have called it 10 in the previous one. But I really don't care about that node. What I care about is Vx, because I just care about the voltage across this. So if I do a KCL at Vx, then that is I in equal to I out. So we're going to have our currents. So if you want to, you could label them, but again, it's just going to be Vx to 0 and Vx to 0. So I will just kind of draw some arrows. I'll assume everything leaves. So we're going to have we'll start with the one that you probably know, which is the resistor. So we're going to have the Vx go to 0. Remember, this is basically just a wire at this point, if that helps you kind of visualize it. So we're going to have Vx go straight to 0. So we're going to have nothing comes in. We're going to have Vx divided by 2 leaving, which is the current through this 2 ohm resistor. So that's our I equals V over R. And then over here, we're going to have the current through the 8 farad. So if you wanted to, you could write it as I 8 farads, and then you could sub it out, and that's going to be C, which is 8, dV dt. So it's going to be ddt, and then it's going to be Vx. My pen's dying. Let me grab a new one. All right. So let me just rewrite that equation for you real quick. 0 equals Vx over 2 plus 8 ddt Vx. So at this point, all we want to do is we want to solve for Vx. Now that's not the easiest thing to do, but we can start doing some basic math. So the first thing we're going to do here is we are going to divide by an 8. Now normally you would have multiplied by a 2 to get rid of that, but we're going to try to get this ddt kind of by itself, because that's the issue we're having right now. So we'd like to clean that up. So you won't normally do all these steps. This is just showing you how we're going to get to a certain form that we're going to use a whole bunch. So we divide by 8, which is going to clean it's going to get rid of the leading coefficient. So normally we want to get the leading coefficient in front of our highest order derivative. So in this case, the first derivative, we want to get that down to a 1. So that's why we divide by 8. So I'm going to rewrite this as ddt Vx, and then we're going to have plus 1 over 16 Vx, all equal to 0. So this equation would be what we call in standard form. And later on, so I'm going to ask you a lot of times to get your equations into standard form, and this is what I mean. So we have our derivative first with a coefficient of 1 in front of it, and then our lower order derivative, in this case there's not a derivative here, we go work our way down. And then our constants go on the right hand side. In this case it's a 0, because the circuit was turned off. But later on, this will be a number in, like, I think later sections. All right, so let's continue solving. So we want to solve this thing. Just going to slide this up. All right, so we're going to set these things equal to one another. So dvx dt is equal to negative Vx over 16. And then I'm going to multiply by a dt and divide by a Vx, so I get my Vx's on the same side. So d times Vx, so dvx over negative Vx, or actually you can leave that. You can make this positive. And then we have a negative dt over here, and then 16. So we got our Vx's on the same side. That was the goal of that step, is to get our Vx's on the same side. Now there is a bit of a trick that we can do. So dvx over Vx, that is actually, we can integrate both sides, is what we want to do now. And when we do that, what we're going to get, this becomes the natural log of Vx. And then this side becomes negative t over 16 plus the natural log of some constant. Now you could just write this as plus c, which is what you're used to. So some constant, but we're going to use a in this class. So natural log of a is the same thing as a constant. There's a reason we write it as natural log of a, because we have a natural log over here. We want to cancel out these natural logs and get a regular constant out later on. Just think of it as negative t over 16 plus c, and we're just going to choose a special form of c called natural log of a. It's the same thing. All right, so let's move all this back up. Since I'm running out of room on the bottom of the page. So we have a few more steps. So these natural logs, we can combine them. So when I subtract the natural log of a, over, then, okay. So when I subtract this natural log of a over, then what's going to happen is we're going to get natural log of Vx divided by a equal to negative t over 16. And so at this point, we're almost there. So we're going to basically take the exponent, but put an e underneath both these sides, and so we're going to basically say e to the power of this and e to the power of this. And the e natural log is going to cancel. We're going to get Vx over that a. So now we don't have because we would have had a really weird constant down here. We would have had natural log of c, which is not something we wanted. Equal to e to the negative t divided by 16. And then to get Vx by itself, we just Vx equal to a e to the negative t over 16. And so this is actually the entire response for t greater than 0. So this is our answer. What we're going to learn later is how do we find a, and then and then we'll also find other ways to find this up here. So this form is actually part of, let me find it here. So what you're going to look at later, pull this up. So we have what's called the complete response, the partial response, we have the first order response. So that first order response is, let me go back to my document camera. So the complete response of this thing would be some v, so v is equal to some v particular plus v natural. What we have actually found here is natural. So the natural response, you can think like a tuning fork, so it has a natural frequency. So that's basically what we found. We found the natural frequency. The particular response, we won't have any of those as long as our right-hand side, this piece over here, is 0. It's tied to whatever this is here. So until we actually add in some kind of an actual source, we won't have anything on this right-hand side. So we won't have any particular responses for right now. So V natural comes in the form of a e to the s1 t. And so this is one of the key equations you're going to want to write down. And so generally, we don't go through all of this work of taking the natural log and derivatives and integrals and all that stuff. We just say, we know that these equations always wind up in this form. They always wind up with some constant a, some root s1, and so we just write it out as this form. In this form, we go find s1 and we find a. So for instance, in this case, that negative 1 over 16 comes from the fact that we have a 2 and an 8 here. 2 times 8 is 16. That's why there is a 16 on the bottom here. All right, so in the next video, we will actually go and try to use this form to find some stuff.